All right, we're going to continue now with the discussion of asymptotic confidence intervals. So to this point, we have discussed confidence intervals, but in situations where we know the exact sampling distribution of the sample mean or the exact sampling distribution of some other statistic that we will use to form the confidence interval. In practice, that is extremely rare. In general, we won't know the exact sampling distribution of, say, the sample mean. Instead, we will know the asymptotic distribution of the sample mean, and we can use that to form an asymptotic confidence interval that doesn't have exact finite sample guarantees, but has very similar asymptotic guarantees. So let's consider a scenario we've looked at before. We imagine we have n observations, z1 to zn, drawn independently and identically from some distribution f on the real numbers, and we had previously talked about constructing a confidence interval for mu, the population mean under f. We did this when f was a Gaussian distribution function. So let's think a little bit about why this was important and what changes if f is actually not a Gaussian distribution, but maybe an unknown distribution. So in the case that f is a Gaussian distribution, say with mean mu and variance sigma squared, and sigma or sigma squared is known, then we talked about how to get our confidence interval for mu. In this case, we would look at the sample mean z bar n, and we actually know the exact distribution of that sample mean. It has a Gaussian distribution with the same mean mu, and a variance that scales like the original variance over n. So again, mu here is unknown, but we're imagining this variance sigma squared over n is known. And so we can use this and apply that pivoting argument from before to get an exact, say, 95% confidence interval by taking the sample mean and adding or subtracting an amount that is based on the width of its sampling distribution. As a reminder, in this case, 1.96 comes from the 97.5th quantile of a standard Gaussian, and so this 1.96 sigma over square root n is the 97.5th quantile of the sampling distribution of z bar n minus mu. Right, and that is exact because our sample mean has an exact Gaussian distribution. So if f is not Gaussian, then the sampling distribution of the sample mean is not exactly Gaussian, but maybe things are still okay. Maybe we can use other asymptotic tools like the central limit theorem to still help us engage with the sampling distribution of the sample mean and maybe return to some of these results that we calculated before. We're going to talk about now what I'm going to call the Gaussian heuristic, and this is not a formal argument. This is maybe something we can keep in mind that will help us build an intuition for what these confidence intervals should look like. So again, when we have our NIID observations drawn from some distribution f that is not necessarily a normal distribution, we know based on the central limit theorem that the sample mean still has an asymptotically normal distribution. And I'm going to write something here that is super informal. So this statement here, I say the sample mean is approximately distributed as a Gaussian with population mean mu and variance sigma squared over n. And there are ways to formalize this statement, but this, as I have written it, should only be used for intuition, should not be used for formal argument. Intuitively, however, this is what the central limit theorem is telling us. The next thing to note is that generally we don't know sigma squared, the population variance. So instead, perhaps, again, I'm going to do something very informal that we have to be very careful in thinking about, but perhaps we can think about a statement like this. Perhaps our sample mean is roughly normally distributed with population mean mu and variance that looks like the sample variance over n. Now note, the sample variance is a quantity estimated from our data. So again, formally, this statement we have written here does not really have meaning and should not be used in formal calculations. But informally, it may help us build some intuition for how we could construct confidence intervals. So for a moment, ignoring how imprecise this whole argument is, if we pretend like this is a meaningful statement, perhaps we can mirror the calculation we did before in the case that the sample mean had an exact Gaussian distribution. And we can form an interval similarly using the 97.5th quantile of a normal with mean 0 and variance 1, and again, ignoring the fact that sigma hat is an estimate rather than a true standard deviation, and just plug it in here. And one might hope that this gives us something like a 95% confidence interval for the true population mean, even when the population distribution is not Gaussian. We gave an intuitive discussion in the previous slides of how we might think about forming a confidence interval for the population mean based on the sample mean. However, it will be really important to understand the asymptotic behavior of that interval that we just proposed. So to better understand what's going on with that interval and what we might hope for asymptotically, we're going to define an asymptotic confidence interval, and this is a lot like the standard confidence interval we defined before, just noting that rather than being concerned about the finite sample behavior of this interval, we are primarily concerned about the behavior of this interval as the number of observations goes to infinity. So how do we define this? Given a target rate of coverage beta and a parameter of interest mu, we think about a procedure that forms an interval in from our data. So again, this is a stochastic interval. And we call this an asymptotic confidence interval with level beta if the probability that mu, our parameter of interest, is captured by this interval converges to beta as n goes to infinity. So again, how does this differ from the confidence interval we talked about before? Before we said that this had to equal beta, and now we're saying it just has to converge to beta. Sometimes when people discuss this definition, they say that this probability in its limit has to be at least as large as beta. So they would say the lim inf of this probability has to be greater than or equal to beta. For now, we're going to work with this probability has to converge to beta as n gets large. So there are a few things that we're going to have to be careful about when we move forward doing our formal calculations. So the first is something that I think people really want to write and want to use in justifications, but we cannot, and it's just not meaningful. So that is, people often love to try to say something like, the sample mean converges in distribution to a Gaussian with mean mu and variance sigma squared over n. So this is sort of like the heuristic that I engaged with before, where rather than converges in distribution, I wrote a tilde and a dot and said, this is good for intuition, but we have to be very careful here. So why can't we say that we have this convergence in distribution? So when we talk about convergence in distribution, the thing on the right-hand side, first of all, has to be a fixed distribution. This is not. This depends on n. And as n gets large, what we see is this actually converges to a point mass at mu. So again, this statement doesn't really have meaning because the right-hand side is not a fixed distribution. And this is why earlier I talked about zooming in, because the 0th order behavior of the sample mean is that it converges to a point, right? That's what the weak law of large numbers tells us, right? And the central limit theorem is telling us about the behavior of the sampling distribution around that point as we zoom in. And again, that's why we had to think about scaling up by square root of n or zooming in. Now, if we look at this second statement, things are even worse. Not only do we have this n on the right-hand side that's not allowed, we also have a sigma hat on the right-hand side. That additionally is not allowed because sigma hat is an estimator based on data, so it's stochastic. So again, we're not really allowed to have any n's or anything that depends on the data on the right-hand side of this convergence and distribution. We have to be very careful there. And in general, this is why we stated the central limit theorem in the way that we did. We said, okay, take the sample mean, subtract from it the true mean, and scale it up by square root of n, and that converges in distribution to a normal with mean 0 and variance sigma squared. Right? We had to do this. We had to go through this exercise or jump through these hoops so that on the right-hand side of this, we didn't have any n's and we didn't have anything stochastic. This is, I think, a really important point moving forward whenever we do theoretical calculations, that we really need facility in moving from statements like this to not quite statements like this, but statements that are kind of like this with a tilde and a dot. Zn bar is approximately distributed like this normal. We use that for intuition. We formally engage with this, and then we sort of do calculation that moves us back towards what we sort of wish we had up here. And hopefully, as we do calculation in this lecture, that becomes a little bit more clear. So the first thing we're going to do is we are going to imagine that sigma squared is known. This is going to simplify the calculation a little bit. We're going to use the central limit theorem up here, and we are going to show that, again, if sigma squared, the variance, is known, then if we define our interval, essentially as we did in the case that f was a Gaussian, we get the correct coverage. So again, if our interval is centered at z bar n, and if we define a half width of our interval as this phi inverse beta tilde sigma over square root of n, then we end up with an interval that asymptotically has correct coverage or coverage related to beta tilde. One small piece to note here, you'll notice we have a beta tilde in here where we have a beta that's not quite beta tilde down here. What is going on? Well, this is like if we want, say, a 95% confidence interval or asymptotic confidence interval, we know from before that we looked at the 0.975 quantiles. So again, this should look very, very similar to the calculations that we were doing before in the case that f was Gaussian, right? The intervals should look essentially identical. Now we're going to formally show this. All right, we're going to prove that result about the asymptotic coverage of in two parts using two claims. The first claim just says that we can reduce the probability that mu is not in that interval to two pieces. And then for the second claim, we're going to look directly at the probability of each of those pieces and see what they converge to. So for that first claim, if we think about what can happen, mu can fall outside of the interval for one of two reasons. Either mu can fall below the lower bound of the interval, or mu can fall above the upper bound of the interval. So these two events are disjoint. Mu can only do one of these at a time. Either mu is below the lower bound, or mu is above the upper bound. Both can't happen simultaneously. So the probability that one or the other happens actually reduces to the sum of the probabilities that each happen. All right, so now we have reduced this to looking at the probability that mu falls below the lower bound of the confidence interval or equivalently above the upper bound of the confidence interval. The proof of these two results will look identical, so we're just going to engage with the top one. To begin, let's graphically look at this event and try to better understand it. So if we imagine we have a number line, we have z bar n here. Let's call this value delta, right? This is the half width of our confidence interval. So the event we are interested in is this event that mu falls to the left of z bar n by at least an amount delta. So it's really that mu is in here, this region. Now recall, mu is actually a fixed value, right? Mu is not random, z bar n is random. So let's pivot this image in our mind and let's think about a sampling distribution of z bar n around mu, right? So this is the sampling distribution of z bar n. We can now draw a similar half-width delta above mu, and an equivalent event to what we showed on the left is this event on the right, that z bar n is to the right of mu plus delta. Right, so again, these two events are equivalent. This is the event that we are explicitly talking about in this statement. However, viewing it in this way will be easier for us to engage with and understand the probability. All right, so algebraically, what this is saying is that the probability that mu is less than z bar n minus phi inverse beta tilde sigma over square root of n, that this is exactly equal to, just with a little bit of arithmetic, the probability that z bar n minus mu is greater than phi inverse beta tilde sigma over root n. Right, and again, if we think about this, this is basically talking about the distance between z bar n and mu, as opposed to asking some statement about mu in relation to z bar n. And this is just very straightforward arithmetic. So now we're going to scale up both sides of this by square root of n, and we get that this is equal to the probability root n z bar n minus mu is greater than phi inverse beta tilde times sigma. So as a reminder, we have that this quantity converges in distribution to a normal with mean 0 and variance sigma squared, right? Just by the central limit theorem. And this quantity here is the beta tildeth quantile of that normal, of a normal with mean 0 and variance sigma squared. So that means, by the central limit theorem, this converges to 1 minus beta tilde. The probability that a normal with mean 0 and variance sigma squared will be greater than its beta tildeth quantile, right? And this is just the definition of that quantile. And this completes the proof. So essentially, all that we did here was we took this original statement, right here, and we pivoted and we zoomed in such that we had a statement we could apply the central limit theorem to. And then from that, we obtained our result. Now, by combining claims 1 and 2, one can show that the coverage of this interval, In, converges to precisely what we claimed on the previous slide. Now, things get a little bit trickier. We're going to engage with the fact that we don't actually know sigma squared almost ever. So what do we do instead? Well, we can estimate sigma squared by this sample variance, right? And equivalently estimate sigma by the sample standard deviation, the square root of the sample variance. And now we might think, well, what happens if instead of using sigma in our confidence interval, we just plug in that estimate sigma hat n, right? And recall that this estimate sigma hat n is consistent, does converge in probability to that true sigma. So maybe we hope that asymptotically things will still work out and we'll still have an equivalent result to before, that this interval will still be an asymptotic confidence interval with level, again, not beta tilde, but this transformation from beta tilde to beta, where you take that tail probability and you double it. So again, how do we think about doing this calculation? One thing we might want to write but can't is that square root n times the sample mean minus the true mean converges in distribution to a normal with mean 0 and variance sigma squared hat sub n, right? We're not allowed to write this because on the right-hand side, we have a stochastic quantity. We don't have sigma squared, we have sigma hat squared, right? And we're not allowed to have sigma hat squared on the right-hand side of this convergence and distribution statement. So instead, what we will generally try to do is move anything stochastic from the right-hand side to the left-hand side, and the kind of statement we might be interested in is something that looks like this. Now, rather than square root n zn bar minus mu, we have that same thing, but divided by sigma hat n, and we have this question, does this converge in distribution to a normal with mean 0 and variance 1? One thing to note is that we would have right? We do have this. Here, rather than sigma hat, I've just plugged in sigma in the denominator. That would be relatively straightforward to show using the central limit theorem and the way that variances scale when you divide by constants. So again, we have this. The question is, can we put a sigma hat in here and still end up with the same result? And again, we're doing this because we are allowed to have as many stochastic elements as we want on the left-hand side of a convergence and distribution statement. We're not allowed to have them on the right-hand side. To show this, we're going to use a theorem called Slutsky's theorem, which we mentioned before. We mentioned an additive version before, and now we're going to engage with a multiplicative version of that theorem. So in this multiplicative version of Slutsky's theorem, we imagine we have two sequences of random variables, xn and yn. We imagine that xn converges in distribution to some random variable x, and that yn converges in probability to some constant c. And in that case, the product xn times yn, which is a sequence of random variables, will converge in distribution to x times c. And in addition, if C isn't 0, rather than thinking about the product, we can also think about the ratio of xn over yn, and that will converge in distribution to x divided by C. Right? And that's going to engage directly with what we were thinking about before, where we wanted to take the left-hand side of the usual central limit theorem statement and divide it by the sample standard deviation. Right? The sample standard deviation is sort of like a yn here. It is a random variable that we know converges to the true standard deviation. We've shown that before. And so what this is saying is, great, we have a random variable that converges in distribution, the usual term in the central limit theorem. We have a random variable that converges in probability. I guess I should really be down here. And doesn't converge to 0 because we're assuming the standard deviation isn't 0. So the ratio of those two converges to the original limit divided by whatever this yn converges to, the standard deviation. So then this confirms and gives us that if we look at this statement that is now scaled by the sample standard deviation, that will converge to a normal with mean 0, and here the variance is 1. The variance is going to be sigma squared over whatever this converges to squared, and we know this converges to sigma. So again, this Slutsky's theorem combined with the central limit theorem gives us this very nice result that is very commonly used in applied statistics without anyone really discussing that often Slutsky's theorem has to be combined with the CLT there. This leads us to the fact that if we look at the interval from before, where again we have now swapped out the true sigma for our estimate, sigma hat n, that this does give us an asymptotic confidence interval with the right level of coverage. So let's just really quickly work this out. This result is going to work very similarly to the previous result we showed. So again, let's work with this first statement, the probability that mu is less than zn bar minus phi inverse beta tilde, now sigma hat n over square root n. So a little bit of algebra here actually shows us that this is precisely equal to the probability that square root n zn bar minus mu over sigma hat n is greater than phi inverse beta tilde. And again, this was just a little bit of algebra. In our minds, we can think of this as pivoting from the original statement towards a statement about this sampling distribution that we now understand. Right? And so we know that this converges in distribution to a normal with mean 0 and variance 1. Right? And this is the beta tilde quantile of that same normal with mean 0 and variance 1. So that means, based on the definition of convergence and distribution, this will converge to 1 minus beta tilde. Again, because we're looking at the probability of exceeding that quantile. If this was a less than, then that would be convergence to beta tilde. So now we're done, and I think one thing worth noting is that often we will see calculations where the left-hand side is converted to a form like this, where we are thinking about looking at a zoomed-in version of sample mean minus truth divided by estimated standard deviation. Now, this is very common because we know asymptotically that this converges to a normal 0, 1, and then we can do all our calculations involving a normal 0, 1. I find it a little bit unintuitive to start calculations here because often this isn't actually the quantity that we initially care about, right? The quantity we initially care about is up here. So I often like to draw a diagram or a picture relating this quantity to this sampling distribution that we know something about, that we understand with regard to convergence and distribution. All right, so what have we shown? So we've shown that if we have random variables drawn IID from a distribution that's not necessarily Gaussian on the reals, and that the mean, the population mean, is our parameter of interest that we are looking for, and the variance, the population variance, is bounded, is less than infinity, then we've shown how to construct a confidence interval with a pre-specified asymptotic coverage for that population mean parameter. Right? And in fact, we've shown that if you use the sample standard deviation or any estimator that's consistent for the standard deviation, then you get the correct asymptotic coverage. And we'll see when we talk about asymptotically linear estimators that this can be used actually incredibly broadly, and almost any estimator that has an asymptotic normal distribution can leverage this idea to construct a confidence interval for whatever parameter it's targeting. So again, this feels specific to population means and sample means right now, but we'll see that it's actually very, very general and an extremely useful tool in asymptotic statistics.